Alright, you guys, so today we're going to go over Elements of Programming Interviews 14.3, find the k largest elements in a binary search tree. So we have to write this function, find k largest in binary search tree. We're given a tree, which is a binary search tree node, a k, so a number to the number, like the length of our, k will be the length of the list that we return. So let's look at a few examples. Say we're given this binary tree and we want to return the two largest elements. So it's easy to see we want to get 12 and 15, and same here, if we return the two largest elements we want 5 and 6. So let's think about some intuition about what we're doing when we, like, how do we recognize, how can we turn our intuition for recognizing the two largest values into code. So the game plan is to first try and come up with some solution that works. Could be brute force. We'll talk about pseudocode, time space complexity. Then we'll try for an optimized solution. So we'll do pseudocode, time space complexity, and then we'll implement it in Python. So let's think about this. Okay, so if you know depth first search, an in-order traversal of a binary search tree will return the values from lowest to highest. So it'll return 6, 7, 8, 12, 15. So if we have that list, the list of all elements in sorted order, we can return the last k elements of that list. So say k is 2 here, we get the sorted order from an in-order traversal. We could return the last two elements, which would be 12 and 15. So that would take O of n time, because we have to touch every single node, and that would take O of n space, because we have to store every value in that list. So okay, O of n time and O of n space for our brute force. So what would, let's take a look at what the pseudocode would be for that. Okay. Let's see. How can I maximize? Tmux maximize pane. Oh. Okay. All right, we're gonna do this in this little guy here. So pseudocode function k largest. We're gonna take a tree and k, and we're gonna return a list. So let's think. So here's what we're going to do: an in-order traversal that returns the values in sorted order, and then we're going to take the last k elements of that list. So in Python, if you give -2, so it'll -2 corresponds to the second to last element in the list. So -1 is the last element, -2 second to last, and -k the kth last element. So this will give us the last k elements on our sorted list, which will give us the k largest elements for this tree. So how are we going to do this? We'll make another function called inOrder. We're going to give it tree. And what else? We'll give it a vals, which will set to an empty list to start. We'll say if not tree, if tree is none, we'll return vals. Otherwise, we'll do just a standard inOrder, which is inOrder tree.left, and we'll give it vals. And right as well. So once we've gone all the way to the left, then we'll visit that node. So we'll append tree.data, because we just want the values. We don't care about the node. And why is that? Because if we see our function definition, we're not returning a list of BST nodes, we're returning a list of ints. So we want the data, not the node itself. Okay, so we'll loop through the tree, we'll get a sorted list of values, and then we'll return vals at the end. So Inorder tree returns a sorted list of all values in the tree, and then we'll return the last k elements of that list, which are also the k largest elements. So this one takes, this is O of number of nodes, time and space complexity. Okay, so let's see here, optimize. So if we want the k largest elements, a binary search tree, like if we want the 2 largest elements in this tree, we don't really need to look at the left side of the tree. So it would be nice if we could start at the right side of the tree rather than the left, and work backwards from the largest element. So maybe if we flip the order of the Inorder traversal, so a regular Inorder traversal, the first element it looks at is, let's see, so node.left 6, node.left is null. So the first element it looks at is 6, so the smallest element. What if we flip the order of our Inorder traversal? So we do node.right. Node.right is, for 15, is none. So the first node it will visit is 15 if we flip the order of an Inorder traversal. So we can flip the order of the Inorder traversal and append values, append data values while our list of vals is less than size k. So let's walk through here. So we start here. We say node.right. Node.right is none. Okay, so we append 15. And let's say k equals 2. Vals starts off as empty. So let's do this again. So we start here, node.right. We get the 15. We call node.right again. We get none, so we return nothing. And then we append 15 to vals. Okay, now the length of vals is 1. And we'll say while vals is not full, we'll do node.left. Okay, so vals is still less than 2, so we'll append 12. Okay, so we get to 12. We call node.right, which is none. Let's think. Node.left is none. Okay, so we return. Okay, we get back to 8. And because vals, the length of vals is not less than k, we're just going to return at this point. So we've only touched 3 nodes. Whereas if you do an Inorder traversal, we're touching all 1, 2, 3, 4, 5 nodes. So we've almost cut our search space in half. We went from touching 5 nodes to touching 3. So that's a little bit better. So that's the intuition. Now let's see how can we turn this into code. So let's think about some pseudocode. So we'll say function k largest. We're going to give it a tree, give it k. Oh, and we forgot. We need to have k. How do we know? Because then how do we know? Well, I guess we don't need k here. Okay. So for that one we don't need k. Okay. So for this one, k largest, we're going to, let's see. So we're doing our modified Inorder traversal. So we're going to say k largest tree.right. And when are we going to do that? We're going to say so if len of, and we need give it vals equals this. Okay. So if len of vals is less than k, and we need to handle the case where we get a none value for tree. So if tree is none, return vals. Okay, so if len of vals is less than k, we're going to go down the right side. And once we get down the right side, we're going to check if len of vals is less than k again. Right, so we get to 15. So at the point we get to 15, vals is empty. So we check, we do no.write on 15, and that returns none, because no.write is none, so it returns none. And because len of vals is less than 2, we're going to append 15 and call the function recursively with 15.left. Okay. So we got a couple checks here. So we're going to append vals.append tree.data, and we're going to call this, we're going to go left here. Okay. And we got to get this function call right, so make sure we give it all the values it needs, all the parameters it needs. Okay, let's think about this. So let's walk through an example. Let's walk through an example with our code and see if this is working. Okay, so we're going to walk through this guy. Okay, so let's see. So we're going to keep track of k. Let's say k is 2. Keep track of vals. Let's keep track of tree. Where are we at this moment? So we start off as 8. So we call our first call is going to be k largest 8 2 and vals is empty. So tree is none. We skip that one. If len of vals is less than k, it is. So we're going to call k largest with tree.write. Okay, so tree now is 15. And is len of vals less than k? Yes. So we're going to append tree.data. We're going to append 15. Okay, and we're going to recursively call tree.left, which is 12. Okay, so 12. And okay, so then we come back up here to the top again. We're back to this line. Is len vals less than k? Yes. Okay, so we're going to call tree.write, which is none. None. And if tree is none, we're just going to return 15. Nothing happens with that, right? Like we called tree.write, we called k largest here with none, and it just returns none, and it just, it's not saved anywhere. Okay, so we go back, tree goes back to 12. We get to this line here. And is len of vals less than 2? Yes. Okay, so we're going to append 12. And we're going to call k, and we're going to recurse down the left child, which is none. None. Okay, if tree is none, return vals, and nothing happens with it. Okay, so we go back to, okay, we go back to 15. 15 is done. We go back to 8. We go back to 8. Okay. And so we're here. We called, when we were last at 8, we're returning to 8 now. We were last at 8, we called k largest on 15. So we got that. Now we come to this line here. Is len of vals less than 2? No, it is 2. So we skip this line. And we return vals. So we return 1512. So that's that's the optimized solution. And what is the time and space complexity for this one? Let's see. So O of tree height, we go at least to a leaf node, which is tree height recursive calls. And we continue traveling until we fill up vals. And so that's k additional calls. So let's see. So we want 8, 15, 12, 3. And then what else? Then we call a couple nuns. And we call the children of 12. We call the right child of 15. And we go back to 8, and then we return. So it's O tree height plus k time complexity. And O of so what space do we take up? So vals takes up space. Vals takes up k space. The recursive calls also take up space. And the recursive calls are proportional to tree height. So in this case, there's 3 recursive calls. So space is going to be the max of k and tree height. Whichever is greater, that's going to be our worst case space complexity. In this case, the height of this tree is 1, 2, 3. If we got a k that was 4, then vals would have 4 elements in it. So our space is proportional to vals, or 4 in that case, space. So our optimized solution is better than our brute force. Let's save that. Let's put this here. Okay. And we'll bring our pseudocode down here. Okay, getting everything in order, and then we're about to implement. Okay, so, okay, cool. Yeah, we want to, oops, 11 down, so we want to make sure we return vals here. Okay, so let's do our, we're not going to code up our brute force solution, we'll code up our optimal solution. Okay, so this is what I want. Okay, so let's move my big head. Okay. We're going to say if not tree, return vals. And we gotta add a parameter, call it vals, starts off as an empty list. So we're going to say if len vals is less than k, we want to keep going. If not, we want to just exit out of this. Okay, we're going to call find k largest tree.right k and vals. Call this again, and we'll append vals.append tree.data, and then we'll recurse down the left child. Search for right, change to left. Okay, and we want to return vals at the end. Okay, let's save that. Let's try and run it. Whoa. Uh-oh. What happened? Interesting. So it's saving the result. So the first example that's run is this one, and the result of this one is 5, 6, and so somehow it's saving, like vals doesn't get reset to an empty list. So that's interesting. Okay. How can we do something different? Say vals equals this. Let's try and take it out of here. See if this doesn't help. Okay. Def Inorder. We're gonna change up how we do this, because we got this, so it's basically correct, but for some reason vals isn't getting reset to an empty list, and so that's messing up our next solution. The logic here is correct, but we need to just change how this is working here. Okay, so we're going to debug on the fly. So we're going to get a node. What else? Yeah, we'll just give it a node. See if this works. Inorder, wait, vals, set it equal to empty, and return vals. We gotta call Inorder tree. Okay, so we call Inorder tree. Doesn't really make sense to return anything here, so we'll just return. Okay, let's see if this works. Uh-oh. Oh, we gotta get rid of this. Uh-oh. Shit. Okay. That's okay. We can get some practice debugging here to see what's going on. Okay. Let's see if not n. Search for tree, place with n. Okay. Nope. Okay. Vals. Okay. And we want to call, I'm going to call Inorder. What else? Right. Let's see. There it is, you guys. So we got some practice debugging there and refactoring. So this pseudocode, I believe this is correct, but for some reason vals wasn't getting reset to an empty list, and so that was messing up subsequent tests that we ran. This test runner here, it runs 900 tests, and so after we run test, for some reason, and if anyone knows, feel free to leave a comment. For some reason it doesn't reset, in this case vals, to an empty list. So we refactored, and we're still using vals. We're just removing it as a parameter and setting it as a local variable inside find k largest. So this function in here is modifying vals as it goes along. And so we set vals to empty, we call our Inorder, our revert. It should be like reverse Inorder. We can change this. Call it like, search for Inorder, reverse Inorder. That makes more sense because we're doing right then left instead of left then right. Okay. It calls it updates vals to the correct value, and then we return vals. That has been Elements of Programming Interviews 14.3, find k largest elements. And just as a reminder, our optimized solution has tree height plus k time complexity and the max of k and tree height space complexity. Alright guys, knock out that interview. Stay tuned for the next one.